bom, então vai ser em inglês, mas qualquer coisa pode perguntar em português. Se não dá para ler, por favor, fala. So, this is the first lecture so it's going to be a lecture on functional, so I put integral methods in condensed matter or condensed matter theory. So, the first lecture, I will just give a motivation, like, or will try to tell you what you can expect from this lecture. So try to give motivation of what we are going to do, and then also say what we are going to do. So this is not still entering into the matter. And then the next lecture on Wednesday, then we really start going into details. So first, I just want to motivate the lecture, which is functional integral methods. I don't know. I think the title was functional methods, and then condensed matter theory. So let me just start with a brief outline what we're interested in condensed matter physics, usually. So the objective in condensed matter physics is, well, to understand different phases of matter and understand here means typically we are interested in understand, or typically we are studying thermodynamic or transport properties. So one typical example will be that some experimental colleague makes some measurement, thermodynamic or transport measurement on some material, and we want to understand this. So then the theorist wants to try to model what he finds, or the other way around, the theorist has some idea, makes some predictions, and says, well, if you go to the laboratory and make some kind of measurement, which will be typically a thermodynamic or transport measurement, then you should find this. Now, the different phases here also includes different phases, so this would be the properties, and also their transitions. So we are also interested in phase transitions. And these phase transitions now generally will be of finite temperature phase transitions, can be finite temperature transitions, or zero temperature transitions, or zero temperature. I mean, we never really get to zero, but it's what is called quantum phase transitions. And more recently, we are also, the last 10 years, the concept of topology invaded condensed matter physics, so we are also interested in topological transitions. Examples. Now, the guiding theme why condensed matter theory or condensed matter physics is very interesting, or at least what I find quite fascinating in condensed matter physics is can be summarized in a phrase that Anderson once stated, which is that more and more here refers to of the order of 10 to the 23 particles is different. So this is a famous paper by Anderson, title of the famous paper by Anderson. And what this means is that typically what we find, or in this case what we find, is an unusual collective behavior which results here. From the cooperative quantum of classical. So this, I think, is what makes really condensed matter physics special or very interesting, is that, well, the sum of many particles is not just the sum, but typically some new phenomena emerge, and they can be very interesting, and this is really due to the collective behavior. And really the keyword here is emergence. Which means that rather complex assemblies of particles often behave in ways which are dramatically different from just the sum of the individual constituents, so different from individual constituents. And the typical examples here in condensed matter would be superfluidity, superconductivity, magnetism, and so on. So this would be like maybe phenomenological phases first that appear, and that one has to understand from the collective behavior of these individual particles. This makes it very interesting. Now, another thing that emerges, I will also come to this later, which is recently very, very hot probably, is that the low energy physics of condensed matter systems. So you start with a system with many particles, so with many degrees of freedom, but you can totally forget like trying to describe that great number of electrons, whatever in the metal, taking into account and also interaction with phonons, interactions between them, whatever. So somehow you have to filter out the low energy content of the theory, like what is really relevant in your material, what is the low energy physics, how is it described. And so another thing that's quite hot now is the emergence of low energy theories which often show the same symmetries like in high energy physics. So we now talk about Dirac particles, Wien particles, Majorana fermions in condensed matter. And so you have the topic of also of symmetries appearing at the low energy content of the condensed matter system. So this is very interesting, and I mean, one of the great tasks of the condensed matter series is to actually understand what is really the relevant low energy physics for a given material. And as said, so it can be in either direction. So either experimentalists make some discovery, high-TC superconductors, and we want to understand why certain materials are superconducting with a high-TC, or the other way around, like it was in the topology insulators. Like people said, well, there are some symmetries or some topological properties which should lead to very striking effects, and which were later on measured. So this then brings me to, so this was very probably superficial in general about condensed matter physics. So you just write down what I said about condensed matter theory. So the task in condensed matter theory is to identify the relevant degrees of freedom for a given or predicted phenomenon, and then to analyze the interplay. And to make it a bit more concrete, I just write down a couple of typical Hamilton operators that we use to model systems, just to give you some idea what would be the typical models that we start out to describe microscopically some theory, and from which we then want to arrive at effective theory. So the typical Hamiltonians of the following form. So taking the Hubbard model, we give them Hamilton operator. Just write down and explain what the different parts mean. Hubbard model. Okay, so now first you have to ask, like, you are all familiar with second quantization, no? Okay, so this would be a typical model where here sigma refers to the spin index, so you have spin up and spin down, and here ij corresponds to some sites on some lattice. So you have here, make a picture, you have some d-dimensional lattice, let's say, where on each side you can create electrons, and the first term will be just describing some kinetic energy term, which describes hopping here between nearest neighbor sites. That's the kinetic term, which describes nearest neighbor hopping on some lattice. And then you have the second contribution here, which is the on-site interaction. Which here, so this is just a local interaction, so due to Pauli principle, you can only have interaction between spin up and spin down. I mean, you cannot have the same site occupied by the same spin state. So this would just penalize like double occupancy on some sites. So this would be a very typical model, which would now describe, so the C dagger in C would be, for example, describe creation and annihilation operators of electrons in the solid, but it can also be called atoms, or fermionic or bosonic, in an optical lattice, and so on. So this would be some typical problem where now you have many electrons in some solid which interact, and you somehow want to find the relevant degrees of freedom which describe the low temperature, low energy physics, which in this case, for example, can be magnetism or whatever. So try to find which are the relevant low degrees of freedom to then map this problem in terms of electrons onto some problem effective degrees of freedom, which then can be very different from these electrons. So I said, so recently a large focus was only on this lattice. So if you look at this and just take the interaction to zero, it seems like a rather boring problem. But I mean, said so recently, there's been a lot of focus just paying attention to this lattice here. So this lattice can be very interesting, like in graphene. So in graphene, you will find that the electrons, which describe the low energy physics, then follow some Dirac equation. Now, recently there's the idea that you can have also wire fermions and so on and so on. Okay? So you can have some additional symmetries appearing when you go to the scales you're interested in. Yeah? So although this looks quite boring or simple, it can be very interesting. Now once you introduce interaction into the problem, then actually it gets really, really complicated. And another thing that makes the problem very interesting is that typically in the condensed matter systems, you don't have like this clean lattice structure, but there's also some disorder in the system. So another typical problem that people study is the Anderson model, where now you have non-interacting system, where again you have some, let's take your spinless electrons, let's say, where you have again a hopping term, and then you have some on-site energy, which here in this model is just taken as a random number. Let's say from some energy interval. So this random energy here would correspond to disorder, okay? So you have some imperfections in your material which disorder your system. And this would be the Anderson model. And it turns out that the disorder, okay, so first we said, well, the lattice structure can already lead to some interesting phenomena. So there can be some topology then related to band structure which gives rise to interesting phenomena. But if you still talk about the non-interacting problem and you introduce some disorder into the system, it can lead to completely different physics. Also very interesting. So you can have all the physics of Anderson localization. That the material becomes insulating just because of interference effects. Okay, so this is again something which, in the end, you don't want to describe, for example, by just talking about electrons moving in some disordered environment, but like as a theorist, you would try to map this problem of, let's say, electrons moving in some disordered landscape to some effective theory, where then it turns out that the degrees of freedom are some kind of diffusion modes, and they start to interact, and this interaction then leads to localization. Just, I mean, very vague, but to give you some idea. Okay, so again, start from some problem which might look first glance not that interesting, but it turns out that low energy properties can be quite intriguing, and the question really is how to model this, how we get to the effective theory and analyze effective theory. Now, just maybe one comment. So I said that one hot topic is at the moment talking about just this part here, because there's some band structure of the electrons which can some topological properties. Now it turns out that also the Anderson insulator, so what I said, that disorder can, so add disorder to the problem, turns out that, for example, in low dimensions, then your system which was metallic without disorder can become an insulator due to quantum interference. But also this insulator now can have some topological structure hidden there, and which again has some interesting affects some interesting properties. Another problem is if you now add to this here interaction. So this would be another very hot topic at the moment. This is, let's take this disordered system. We said, okay, if disorder, let's say, is strong enough, you can make out of your metal an insulator. This means that somehow the degrees of freedom here, the electrons do not explore the entire material anymore. So you don't have like ergodic exploration of the entire system. Now, typically, what we think, like in statistical mechanics, is, well, but if you take this system, this disordered system, and make it completely isolated from the environment, and then if you turn, or let me state it differently. If you take the system with disorder, and then first you couple it to some environment, so you have some interaction with some gas, or you have interactions between the electrons. Now you add this interaction term. Then what will happen is that typically the system will get ergodic again. So you can describe it by usual statistical mechanics. Okay? So while yes, in the non-interaction case you can have some localization, and once you introduce a coupling to a bath or interactions, the system should become ergodic again. Now, a very hot topic at the moment is also consider now the case that you start out from this disordered system, which is where you have localization, which is non-ergodic. Now decouple it from completely the environment and just let these, let's say, electrons or all atoms in some trap, allow them to interact with each other. So take an isolated quantum system with some disorder, but intact. So typically also, like what we assume as well, interaction should be enough to make the system completely ergodic and then allow it to describe by statistical mechanics or statistical mechanics. But then it turned out, there is work that this doesn't always have to be the case. So actually you have some, you can have some critical interaction strengths below which the system will stay non-ergodic, localized. And then there's some phase transition to an ergodic phase. So this is also very, it's like many body localization, which is also very hot at the moment. So although these models look very simple or not that interesting, there's a lot of physics hidden in there, and it's, well, it's hidden in low energy part. Okay, so it doesn't make sense to think about like many degrees of freedom, but you have to somehow get a feeling what are the relevant degrees of freedom, filter them out, and then you will find like interesting things emerging, happening there. Okay, so this was Anderson model in a discrete way. Well, you can also have the Anderson model, let's say, in a continuous way. Just write it quickly down. So where you have now, let's say, electrons moving in some, so you have some kinetic term here, some d-dimensional system, and now the disorder would be just described by some potential V of x, which is now a random function. So it just describes here random potential. So maybe I state just one more system, because probably this will be also or one more model which should become interesting throughout the lecture, which would be just a system where, let's say, you have one degree of freedom coupling to another one. So this would be like electrons in some solid coupling to phonons. So we have here the kinetic term for electrons, so you have some dispersion Epsilon P. This is just the kinetic term for the electrons, so this would be the Fourier transform of this one here. And then you have the second part, which now describes, let's say here, some photonic degrees of freedom, which are phonons in a solid. So this is creation and annihilation operator of different types of phonons indexed by the J, and this momentum Q, where omega of Q is the dispersion relation. And then, so this would be just two independent systems where you have the kinetic energy of electrons and photons not interacting, not speaking to each other. And then you have some interaction between them, so some coupling, which can be of this form here. So you have some coupling constant for J's degree of freedom. So you have J can be some number 1 to n in different phonon modes. This is a coupling constant for J's mode, phonon mode. And what you have here is described an interaction between electrons and phonons, where what happens is you destroy some electron with a momentum k, and you create a momentum with momentum k plus q, and this occurs by absorbing, for example, a phonon with momentum q. Yeah, so just one diagram. Afterwards, we'll come to find the diagrams and all this, but you can think of this like this. You have an electron with momentum k. This absorbs some phonon with momentum q, and then propagates with some momentum k plus q. Okay, so this describes an interaction between the electrons and the phonon, and this, for example, can then lead to superconductivity, which we will discuss. This is the usual PCS theory for superconductivity. Okay, and then of course you have many more models. So in a real system, like where you have superconductivity mediated by phonons, there can be also disorder, so you want to understand the role of disorder and so on and so on. You can have competing interactions between electrons. So there's many more models, but this was just to give you an idea of that. So then, as already said, but just maybe write it down. So often we are not interested in dynamics, for example, of the individual electrons in the solid, but of an effective degree of freedom, which describes the collective phenomenon that describes and this can be, for example, the Cooper pairs in a superconductor, effective magnetic moments, and so on in the magnet. Moments, and so on. So, as I already said, the key word here is then low energy effective theories. Effective theories, that's what we are after in theory. Or often, this is what we are after in theory. So derived from a microscopic model, an effective theory, of the relevant low energy degrees of freedom. And I hope that after the lecture one will have more or less clear what, like, one procedure would be to do this. Degrees of freedom. This will be maybe one guiding theme in the lecture. So this, of course, first of all means that somehow you have to have a feeling of what then are the relevant low energy degrees of freedom. So I come back or come to this like short. So we will use some functional integral methods to derive the low energy effective series because they are quite efficient in doing this. So the first thing that actually you have to find is you have some problem described by some kind of macroscopic Hamiltonian, which I wrote down, and you have to get an idea what are the relevant low energy degrees of freedom for the problem. You don't want to talk about electrons anymore, but you want to describe the system in terms of some effective or some collective degree of freedom. So first step is to try and start analyzing the model to get a feeling of what will be the relevant degrees of freedom. And this will be maybe the first more physical part of the lecture. So in the first lectures we will just construct functional integrals because this will be an efficient language. Now after we have constructed first functional integrals, we do exactly this, trying to identify low energy those are relevant degrees of freedom. And this is typically what you can do is you can try to start out from some perturbation theory. Like start out from the Hubbard model, which was written down there, and say, well, let's take as a reference point the non-interacting theory, and then try to see if we can see if something interesting happens if we do perturbation theory in the interaction. So, for example, in the BCL theory, you will see that if you make so you start out from, let's say, this problem, and the first thing here is to, let's say, integrate out the phonon degrees of freedom, which will then generate some interaction between the electrons. So just as here, so an electron can absorb a photon, so if you integrate out photons in some way, you can think about the interaction process of electrons exchanging a phonon, okay? So this would be then some interaction process. I mean, to give you an idea. So then you will have here some microscopic model of interacting electrons, and you can try to see what happens if you make perturbations here in the interaction. And then you will find an instability that tells you that something interesting is happening. If you make an analysis of this instability, you will identify the relevant degree of freedom in which you then want to construct an effective series. So this will be more or less an illustration of the program that we are going to follow. So first, try to construct functional integrals, because this will be the method. Then the first thing will be to do some perturbation theory. So I will introduce you to Feynman diagrams based on the functional integrals. And then after we have some idea how to do perturbation theory, then we want to see how one can really construct the effective series. Okay? Will then be the next step in the lecture. So constructing functional integrals, and perturbation theory, and then construction of effective theory. Now, this may sound as a rather straightforward program, but it is not. So this problem of identifying what are the relevant degrees of freedom that describe whatever, for example, experimentalist measures in the laboratory, can be really, tantalizing difficult. So it may sound easy, but this in fact can be tantalizing difficult to understand what are the relevant degrees of freedom at low energies, which lead to the phenomenology that you're finding in the laboratory. One famous example of this is the high temperature superconductors, where you find an experiment for the phase diagram. So this is typically, for example, cuprates material. So you have a phase diagram spanned by two axes. So one is the temperature and one is the doping of the material. So here is the whole doping. So we have, say, a very low temperature regime and then the high temperature regime. So many of these materials, if you don't introduce any dopants in the system, you will have an antiferromagnet. Then there is a famous superconducting dome. So it's a dome-like structure here where you have superconductivity. So you start out from some antiferromagnet, and if you dope enough your antiferromagnet, you will come to a superconductor. Now, in between here, it's not so clear if you maybe have a spin glass phase or whatever. Now, if you go above the temperature, above the critical temperature, where superconductivity breaks down, so you have here this dark line, where there's a so-called pseudo gap, which is a weird phase that is not really understood. There might be some charge density waves appearing also. So only at the very large doping you have a Fermi liquid. But what is actually here happening in the pseudo gap is not clear at all. So here, for example, you really want to understand what is driving the superconductivity in these cuprates by doping. So since you start out from an antiferromagnet, you may think that, well, the spin fluctuations can somehow then drive the blue for the superconductivity, but it's not that simple as that. So there's weird things going on above TC which are not really understood, and really the problem is here to understand what are the relevant degrees of freedom in this model. So saying here, well, start out from your microscopic model and then derive an effective theory. So this is more or less described by Hubbard model. So this can be really, really hard. It's not so clear if it's the interplay between different degrees of freedom and so on, which leads to this rich physics. But then again, this is also the interesting part about condensed matter theory. So then, just take one more statement here on emergence, which I also said. So you can have a very interesting rich physics appearing. Starting out from this, what might at first glance seem as quite simple models. And the other thing that I already meant is also a topic that's been very interesting or has attracted a lot of attention in the last 10 years maybe, started 10 years ago, is all the idea that you can have low energy physics of your system now is described by equations which have different symmetry properties. So nowadays find many condensed matter physicists talking about Dirac-Weil or Majorana fermions. So we have in some theories you have a supersymmetry emerging at the low and in the low energy effective theory. So this all makes also again condensed matter theory or condensed matter physics very interesting, I think, because the low energy theories that you're after can display the same symmetries as those models that are studied in high energy physics. interesting because you can have realization of like models that were first studied in high energy physics, and then maybe at some point they were just not considered anymore because they weren't considered relevant, like the Weyl fermions or whatever, and then suddenly you see that, well, in the condensed matter there exist materials where they naturally pop up as the relevant degrees of freedom. So this is very interesting, and even maybe in the condensed matter systems you find even more rich physics than previously considered in high energy physics, so there's even more interesting maybe symmetries and structures appearing, which is really quite fascinating at the moment. So I don't know. Maybe we can. Yeah, maybe we can try also to make some exercises, just giving a little introduction to topological isolation or whatever, because it's going in this direction. Yeah, I have to think about it. So, but having said this, I think there's another very fascinating thing, which is that you have, in a way, some unification of high energy and low energy physics. So nowadays it's quite usual that high energy physicists also write papers which then appear on ConMat, on the condensed matter theory server, and so on. So this is very nice. It's very interesting. So you have some unification between high energy and condensed matter theory. But this also means that, well, if you have some unification, you also want that the people can talk to each other, no? So I would say that one of the unifying languages between the fields, well, is just the field theory. So field theory can be seen as one language that both communities can talk. And so, I mean, by now, I mean, you know that also condensed matter theories talk about Goldstone modes, Goldstone bosons appearing in superconductors, and so on and so on. So this is very nice, but this means that I think, like if you want to do modern condensed matter theory, you should also be familiar with concepts of field theory. So and this then brings me to the goal, which I write on here of the lecture. And then you'll see, I hope you get close there. So having said all this about condensed matter physics, now let me say what actually I would be happy to achieve in the lecture. So the objective of the lecture is that you learn standard field theory methods that I usually use in condensed matter physics. And learn, as I said here, would also mean that we try to include some exercise sections always. Okay, so we have to see like in which rhythm we are going to do it, but I will always provide some exercise sheets because it's really essential to sit down and do some calculations by oneself. Like I always say, but I mean in my case it was I was attending lectures and I didn't understand anything, not everything, but you think like it's you more or less got the idea, but once you really sit down, you realize you didn't understand anything. Okay, so then you really have to start thinking in a different way. So it's very important to make exercises. So as I said, so probably we make out of 4, we make 1 exercise section, or let's see how it works. So I will always distribute some exercises, and then we should gather together and then just discuss it at some point. Okay, so this was all about, maybe I should have left with the title, which is talk, which is functional integral methods in condensed matter theory. So this was all about what is condensed matter theory about. Okay, so this was the motivation of the second part of the lecture. The first part of the lecture was, the first part of the title was functional integral methods. So let me just also motivate then the first part of the title. I don't know, how do you want to do it? I mean, so today it's a light lecture because we don't do any details, any calculations. It's more just talking and like giving an idea. So once we go more into detail, I will always make a break because I think it's good like to make whatever, 45 minutes, 1 hour, and then 10 minutes break. Now I could also today do like 5 or 10 minutes break, or we just continue, like any preference? I mean, it's just... Okay. Okay. So then let's talk about the first part of the title, functional integral methods. So let me just state here briefly that there are, let's say, at least 2 approaches to quantum mechanics. Let me just use QM for quantum mechanics, and QFT, which is quantum field theory, okay? Which is the operator and the functional integral method. Now, obviously, I mean, this is clear from the title, we stick here to the second option. So there might be other courses here at CNFF where maybe quantum field theory is introduced in terms of operators, but I actually never really learned quantum field theory in terms of operators, but always started out from function integral representational form, and I think it's just much more convenient, much more just, I mean, once you sit down and then start working yourself, I think that's, at least I think it's more convenient way to address problems. So, but just to make this maybe a little bit more clear here, so let me just briefly talk about quantum mechanics. So where we study the behavior of single particles which are viewed as point-like degrees of freedom. They're, let's say, zero-dimensional objects. So we can describe these particles, so typically by some momentum or some coordinate representation. So the operator approach, we go to some, let's say, x or p representation, which is for most problems the most convenient. Then look at the Schrödinger equation for the wave functions and try to solve this wave functions. Okay, so this is like what we do in the operator form of this. Now the alternative way is Feynman's approach to quantum mechanics based on path integral. Where I will also come to this briefly. Actually, the main object of interest is the so-called propagator, which is a matrix element of the time evolution operator. I'll come back to this like in a second, but let me just write it down here. So you have the time evolution operator, which tells you like how the system evolves from some time t prime to t, and you may consider matrix elements in the X representation of this object. And the Feynman path integral constructs the propagator or matrix elements of the propagator as integrals over, let's say, histories. This is just very superficial to give you some idea. We'll come back to this in detail. Where history now refers to one-dimensional trajectory, which the point-like particle, the zero-dimensional object, if it makes some trajectory in, let's say, space, then this kind of trajectory can be viewed as a 1D path. So instead of going to some, let's say, X representation, write down the Schrödinger equation for the wave function, trying to solve it. The Feynman path integral directly studies the matrix element of the time evolution operator, the propagator, and represents this now as integrals over histories which are now one-dimensional objects. Okay? This is a very brief summary of the idea of the two different descriptions of quantum mechanics. Now, generalizing this one comes to the two different descriptions of quantum field theory, which instead of a single particle studies infinitely many degrees of freedom. In the sense that you can create and annihilate particles. So instead of considering zero-dimensional objects or point-like objects, you here consider fields described by some, let's say, degree of freedom phi instead of, let's say, here some coordinate x, which, depending on which problem we exactly look at, can take values in some target manifold. And the typical examples that one has like scalar fields, where phi is just from R or from C, or it can have some vector fields where it's from Rn or Cn. or you can have some more complicated structure, but you have some field degree of freedom. So generalizing, then what was said here about quantum mechanics. Now you can have, on the one hand, the canonical quantization, where we consider canonically quantized field operators. Okay, like here in quantum mechanics, we said we have the two-dimensional degrees of freedom, which we can describe by some coordinate x, and then we introduce operators x and p, and can write down Schrödinger equation in one of those representations. We try to solve it. Here you can introduce a canonically quantized field operators, which then would be some, let's say, operator phi, some conjugate operator pi, and you can study then the Heisenberg equations for the time evolution equations. This would be the operator approach, and the functional integral approach, again, directly typically concentrate on propagator. Where you now write down the propagator of the theory, again, as integrals over histories. Integrals over histories, which again means here integrals as over configurations. The field can take the time. Configurations. If you can't read something, please let me know. So this histories, which are configurations, field can take. Okay? This is very, just superficial, just to give you an idea. We'll come back to this in more detail. But it's just, in a way, the generalization of quantum mechanics, where we said, well, instead of looking at some differential equation, directly look at the propagator and write this as like the trajectories or histories of the one point particle. So this will be lines or paths. So here in quantum field theory, the objects are more complicated. We have fields, some scalar field or some vector field or whatever. So it's some object which lives in some manifold, and now this object also evolves in time. So you add another coordinate to it, like moving the point, you get some lines. So moving this object, you will also get some higher dimensional object, by one dimension higher, and you can then sum over all these histories, or you can represent the propagator of this theory as a sum over these histories. Okay, so this is like the basic idea. Then come in detail to this. So now there's two ways one can go. So what we are interested in is we really want to talk about condensed matter physics. So we want to talk about these Hamiltonians that I wrote down in second quantization and understand how to do perturbation theory for these models and how to derive effective theories. So what we really want to do is we want to talk about quantum field theory. As I said, we want to go to this description here instead of looking at Heisenberg equations for the operators. We want to talk about field integrals. Now, I think it is good, instead of jumping directly here, to make some excursion first, which will be excursion of about 6 lectures, so 3 weeks, which would be first to see how this alternative formulation works, this functional integral method works in quantum mechanics. So first, instead of going directly to quantum field theory, first look at quantum mechanics and see how to construct Feynman path integrals there, and study some simple examples, and also some examples which tell you the power of the path integral. So this is the thing that I would like to do, but this will mean that in the actual lecture or the actual objective that I wrote down, like what you want to see how to construct effectivity, we will lose like maybe 3 weeks. But I think it's instructive. Otherwise you say, well, I don't know if you already know path integrals or whatever, but then we can immediately jump to the quantum field theory. But this would be my suggestion. If you didn't see path integrals, then it may be worth to make this excursion. Is there like any, I mean, does any one of you know path integrals? The formulation of quantum mechanics in terms of path integrals, or just give me some feedback.
I know, but I think it's a good idea to review this.
Okay, so then we'll do this, because I also think it's a good idea. Now there's the reason why probably you didn't see path integrals in the quantum mechanics formulation. This is because like all problems that you solve actually in quantum mechanics, like typically like particle, free particle, particle in the box, blah blah, that becomes terrible in the path integral. So the simple problems turn out to be more complicated in the path integral, but it's still a good investment to look at this, because like in the real world, then you don't want to look anymore at free particles or particles in the box, but at more complicated problems, where then the path integral, I think, is very strong, because it can very nicely formulate perturbations in terms of path integrals. You can also do it in terms of operators, but I think it's more easy with path integrals. But there's other advantages, which is the path integral also is very strong for non-perturbative effects. And there's one example we can already discuss on the level of quantum mechanics, so some non-perturbative calculations using path integrals. So this is one advantage. Another advantage is that it always leaves you very clearly like what is quantum, what is classical. You easily see how the classical word emerges from quantum mechanics in the path integral formulation. Now this is very useful if you're, for example, interested in like there's different areas in condensed matter physics. So one sort of people are also interested in maybe it's not really condensed matter physics, but mesoscopic physics, and then there's this community of quantum chaos. So people are interested in what is signatures of chaos in quantum mechanics. And once you come to these kind of problems, it's very useful to have some theory where you can always like see how the classical world emerges, because then you can first start out studying a semi-classical limit, where you like study classical, let's say, effects, and then consider quantum fluctuations, the effect of quantum fluctuations. So you can clearly see here how the classical world emerges from the quantum world, which means that you have a very good method to describe all the semi-classical effects, and once it comes to problems like quantum case, it's a very effective method. And yeah, so this is, I think, advantages of the path integral. Now, let me just maybe write this down. So why do we stick to the functional integral methods? Maybe I should just talk. So usually you don't want to start introducing quantum mechanics in terms of path integrals, because it's just complicated. This film, but usually so there was one professor once who didn't want to do, who really said, no, I'm going to do different. I introduce like basic quantum mechanics in terms of the path integral. And it turned out a disaster. Like it was a lost semester. Like these guys never like it's just not the way to introduce quantum mechanics, I think. It's like afterwards, if you introduce it this way, you don't get very far. Okay. So why functional integrals? summarize what I said. So they are, once you come to more complex calculations, they are very flexible and often allow for simpler calculations. Oh, I don't know if I mentioned it also. So also, once you go to the path integrals, and actually the connection between quantum mechanics and statistical physics is also very transparent. And I think I will also discuss this briefly, so you see nice connections also between these areas. So it's flexible, often simple calculations now for real problems, like not for the textbook quantum mechanics problems. Then is said you have ways to study non-quantitative facts, and we will discuss an example of this. So we will discuss an example in the case of quantum mechanics, and then, like for us, it's interesting is that it's effective or it's powerful in the construction of effective theories. Just to give you a very superficial idea, well, once you wrote down your propagator or whatever the object that you're interested in as a sum over like field configurations, the construction of effective theory just in a way amounts to a change of variables in this integral. So these path integrals can be viewed as some high-dimensional integrals. So you can always think about like putting your system on some lattice, so it's just some high-dimensional integrals, and then changing to some effective degrees of freedoms means just a change of variables in some sense. So this is called functional integrals. Let's see. Let me okay. Any questions so far or comments? Then I just give you a brief outline of the lecture. So then start with Feynman path integrals. Path integral, PI for path integral formulation. Of quantum mechanics. So this will, as I said, probably be 5 or 6 lectures, so it depends a bit like how it works out. So maybe we'll try to make also one. So I will first, starting next lecture, give you like the general recipe how to construct path integrals, and we will discuss examples, free particle, harmonic oscillator, and then maybe also for the path integral for spin systems, because it's quite interesting also. There's some interesting things appearing there. This, for example, you can make in an exercise, and then I want to give as one example. Oh yeah, then I'll probably discuss, quite simple, one can discuss it at the harmonic oscillator, the relation between path integral formulation of quantum mechanics and statistical mechanics. And then I want to discuss still, let's say, an example of like a non-quantitative calculation in the path integral, which I think is very nice. So this will be, say, 3 weeks. Then we will turn to what we're actually really interested in, and this is quantum field theory. So there we want to see how the construction of the path integral for single particle problem can be generalized to many body problems. And this means that from the path integral you go to the function integral. Of quantum field theory. So there, again, there's different ways to do it. What I will do is just take into account the typical Hamiltonians that we are interested in, like in terms of creation and annihilation, operator quantization. We will construct the many-body function integral based on coherent states. So this is like the common procedure used in, I would say, condensed matter physics. There's other ways to do it in high energy physics, but I will concentrate then more on the condensed matter approach and then directly come to discussions. So once we have constructed the many-body function integral, we will then see how let's say function integral might work, which will first be discussing how to organize perturbation theory in terms of function integrals. This means you start, you have some Hamiltonian which consists of 2 parts. One part is, let's say, free electrons or some problem that you understand, and then you add some term that you want to understand, like interactions, and we will see how to organize perturbation theory around some reference state, which say it also will be example non-interacting electrons you can take as a reference state and then introduce interactions and see how this modifies. And there's a common scheme how to address, like studying the influence of some perturbation in terms of Feynman diagrams. So we will discuss Feynman diagrams. And then the 4th part should be so again, applying function integral, which will be construction of effective theories. And I will try to always discuss these problems with some concrete examples. Now, from here, then the natural way would be to discuss phase transitions, renormalization group, and so on. But probably we don't come to this. But let's see how far we come, and then maybe we can think about some continuation next semester or whatever. Okay, so this is the outline. Just let me give you some books from literature that the lecture is based on, actually. I mean, I follow quite closely the book by Albert and Simons. Which is called Condensed Matter Field Theory. Field theory, which I think, I mean, I very much like the book because I think it's a good compromise between being technical and having applications. Now, a more technical and more detailed book, so sometimes maybe this is, I think this is written very well, so sometimes you're really very much convinced like by the argument they use, but then when you sit down and want to calculate, you see that it might be not that easy. So sometimes you want to look maybe at some more details, and then it's that provides a lot of like details. Here. into many parts of the systems. Another book which is oriented on quantum field theory in condensed matter is the one by Strelick, which is quite interesting, but maybe hard at the beginning, but still one can look into it. So we just add it. So QFT, quantum field theory, in CMD, condensed matter, no, condensed matter physics, and then maybe another book which is not written like, which starts off from second quantization, and second quantization foundation only in the end also discusses path integral, but which contains a lot of nice physics. So you can also look at this just from a different perspective, which is like this Coleman introduction. Questions? Then maybe we can still start like this very brief introduction here. So we want to first look at Feynman's formulation of quantum mechanics. So next lecture we will really go into detail and see how to construct path integrals. So let me just start with a very brief introduction. First part of the lecture, Feynman. Okay, so maybe just one or two sentences on the history. So, I mean, we learn in classical mechanics that actually classical mechanics can be understood from some variation of principle. So we have the principle of the minimal action, which tells us that minimalizing the action we arrive at the equations of motions that then define the classical trajectories for a given problem. And actually in 1933, so in this Lagrangian formulation of classical mechanics, the classical action plays a fundamental role. Also, in 1933, Dirac asked in a paper